We now come to the third case of harmonic forcing. This is the base motion. In the case of the base motion, the base of the mass spring damper system is moved harmonically with a certain displacement, such as y sine omega t, and we would like to analyze and find the displacement of the mass on top of it. So the system is as follows. The base moves in sinusoidally, and then the mass also moves sinusoidally with the same frequency, as we will find. We write the equation of motion as follows. These are the real forces acting on the mass. Spring force and the damping force act on the mass, and mx double, that is the inertia force. So as you sum up all those forces, eventually the model you are going to get will be the following: mx double dot plus cx dot minus y dot, which is the relative velocity, minus kx minus y, and this is the relative displacement. This is equal to 0. Y and y dot are the forcing terms. So in this system, the equation of motion is repeated here. We assume that the base moves sinusoidally. In the case the base moves sinusoidally, if you move the y terms to the right-hand side and take the derivatives accordingly, you get the following differential equation for the system. You have as omega sine omega t and cosine omega t terms here. Addition of a sine and the cosine term can be, as we know from previous lectures, the sine and cosine terms can be combined with a sine term with a phase shift. In that case, the phase shift is so that is given by tangent inverse of c omega over k, and the amplitude of the sine wave is the combined amplitudes of sines and cosines. We had done this before. So we can assume that this is a mass spring damper system forced by a sinusoid with a phase shift. And here is A is the forcing term, as you see. You might think that A is the amplitude of the forcing. Okay. So we will again assume that the solution of this system is another sine wave with a different phase shift. Here it was alpha, now we have a phi. So we have a harmonic motion again, and we can solve for this. It's not too hard. Actually, we just substitute this into our ordinary solution, as we have done before. And as you do that, the ratio of x to y, x is the amplitude of displacement, y is the amplitude of the base motion, you get such a term, k squared over c omega squared, etc. And then you non-dimensionalize it by r and zeta. Okay? In that case, we call the ratio of x to y as the displacement transmissibility, because y is the base motion. If we look at the model, y is the base motion, x is the motion of the mass. And phi is the inverse tangent of a kind of a complicated expression. This is the phase angle of the system. So the graphical representation of this system, of the transmissibility as we have defined in this equation, can be plotted as follows. The transmissibility starts from 1 and it eventually goes to 0 rather slowly. And we have different plots for every damping ratio, as we did in the previous cases. But here we have an invariant point, and the frequency ratio is √2 all of these curves meet at a certain point. And we also have a kind of irregular phase angle term. So the term, if we want to take notes about this, is as follows. First of all these frequency response curves start from 1. The transmissibility is 1 for steady state, that is R equals 0. And if R equals root 2, again, all these curves meet at this point, which is an invariant point. Again, the transmissibility is 1. So the motion of the base and the mass is the same at these frequencies, 0 and R equals root 2 frequencies. In between between 0 and root 2, between these range, the transmissibility, no matter what the damping ratio is, it's always greater than 1. And if R is greater than 1, if R is greater than root 2, the transmissibility is always less than 1. Okay, so that the motion of the mass is less than the motion of the base if R is in the higher frequency range. One interesting conclusion is if R is greater than between 0 and root 2, if damping increases, then the transmissibility will decrease for a certain value of R. But interestingly, if R is less than root 2, if we increase the damping, well, then the transmissibility does not decrease, but on the contrary, it increases. That is, increasing the damping in the higher frequency range does not help you in terms of decreasing the transmissibility. It just increases the transmissibility. So you should rather have smaller damping in this range in order to have less transmissibility. We have an example here. Let's say that we have a vehicle that is on the road, and it just moves on the road, and the road surface is modeled by a sinusoid. The mass of the car is modeled by 1,200 kilograms. The spring constant is 400 kilonewtons per meter, and the damping ratio is 0.5. Let's say that the road amplitude is 0.05 meters, 5 centimeters. Okay, and the length of one cycle, wavelength, this L, is 6 meters, let's say. If the car moves with a 20 kilometers per hour speed, we want to determine the displacement amplitude of this vehicle. Okay, so this is a typical base motion problem. The base of the car is transmitted to the wheel, and there is a shock absorbing system that transmits the motion to the main mass of the car. Let's try to analyze this. First of all, we have to find the frequency of the forcing first. And in order to do that, we need to find the frequency of the road. But we are not given the frequency, but rather the wavelength of the road, which is 6 meters. We can find the frequency in terms of velocity divided by length. So in terms of hertz, the frequency of the road, that is the number of cycles the road makes in unit time, is given by velocity over the length of the wavelength. So it is, let's say, 20 kilometers per hour, but we have to convert that to meters per second, and then divided by length. So it is velocity times 1,000 divided by 3,600. This is in meters per second, divided by 6, or multiplied by 1 over 6. If you want the circular frequency, you will have to multiply by 2 pi. So we get a term like 0.29 V, where V is in terms of kilometers per hour. So the omega in terms of 20, if you multiply it by 20, you get 5.81 something radians per second. The natural frequency of the car is k over m in square root. So if you find that, it is 18.25 radians per second. And the frequency ratio is omega over omega n. So it is 0.31. Now the amplitude ratio or the transmissibility of the car, if you substitute all the values of zeta and r, you find that eventually it is 1.1. So x over y is 1.1, which means that x is equal to 1.1 y, which comes out to be 0.55 meters or 5.5 centimeters. That is, the car has more vibrations than the road. The vibrations are amplified at the speed. But if the speed increases or decreases, the vibration amplitude of the car changes. Okay.